he's a particle physicist by training. Is that correct?
Yes, correct.
Yes. So just this. So he did his PhD in Washington University in 1990. Then he was in Canada and then in Michigan State University for a postdoc, after which he joined the Institute of Physics, Bhubaneswar. And since then he has been there. His primary interests are in particle physics, accelerators, and astroparticle physics. But he has also deep interest in quantum information science. And he will be telling us about, as I said, uncertainty relation and quantum entanglement. Professor Agrawal, please go ahead.
Yeah, okay, sure. Okay, sure. Thank you. Actually, my background is just like Prasanta. Okay, he also did his PhD in particle physics. Okay.
Yes, absolutely. Always, I'm a bit nervous introducing them. Am I saying it right?
Yeah. But he was doing more formal things than me. Okay, my work was more phenomenology oriented. Okay. Yes. So anyway, so actually, from what I understood, okay, from most of people in audience are students. But my talk is not fully pedagogical because I guess this was not my full understanding. But you are free to ask any question anytime. First few slides will be quite elementary, and I think some of you students may not be aware of whatever I'm going to tell you. Okay, about these uncertainty relations. Okay, so first part is more about what they are, and second part is more about some work. Okay, and some of this some of you may have heard of what I'm going to say in the past also. Okay, so let me start with what are these uncertainty relations. Okay, so uncertainty relations, actually, as most of you know, they are known as Heisenberg uncertainty relations. And they were introduced long ago in 1927 by Werner Heisenberg. So he had a paper, The Physical Content of Quantum Kinematics and Mechanics. And actually there is still some controversy what exactly his title was, because some of you may not know that before Second World War, a lot of scientific literature was in German. Okay, so Heisenberg was from Germany, and he wrote a lot of his papers, and his communications were in German language. Okay, even this particular journal was also in that particular language. So this is one particular translation where this word physical is often translated differently. Okay. Actually, the history is a bit, so sometimes different than what we come to know. The things evolve is quite different than the way they are often presented in textbooks. So Werner Heisenberg, actually, at that time, some of you may know, quantum mechanics was basically invented in 1920s, right? And as you read in textbooks, Heisenberg first introduced what is known as now matrix mechanics. And then 1 year later, it was Schrödinger who introduced his equation, Schrödinger equation. And Heisenberg was not into how to visualize what is happening. And he was more interested in describing the phenomena. In particular, they were interested in transition in atoms at that time. While Schrödinger was more interested in giving some picture, how to visualize a particular process. And so this wave mechanics and matrix mechanics, they were there, and Schrödinger showed they are equivalent, but somehow Heisenberg was slightly disturbed what this wave mechanics means. Okay, so he was trying to understand what is this physical or visual content of quantum kinematics and mechanics. Okay, and he used some at that time what is a semi-classical reasoning to propose some kind of relation between between the momentum possibility. What is uncertainty in momentum measurement and position measurement. But actually, this idea, there is something called uncertainty relation. It got hold of the imagination of many, even people who were peripherally interested in science. So this relation has now transcended. Okay, whatever the original scope was, Basically, this was a limit on the knowledge of two quantities. If when you measure them simultaneously or even without simultaneous measurement, okay, you don't have to do that. So I mean, originally it was introduced in the context of measuring momentum and position of a particle, in particular an electron. I mean, this was what Heisenberg was interested in. But now, through the popular science books, this whole idea of uncertainty relation has become part of, you can say, collective consciousness of those whoever are interested in science. I mean, you will often see its a discussion in totally different context, totally unrelated to original idea, in various branches of knowledge beyond science. Basically, it is a kind of trade-off relation. Okay, what if you want to know some particular quantity well, then how will it affect the knowledge of another quantity? In that sense, it has been used it has been discussed, or it has inspired many type of trade-off relations, even as I said, beyond science. Okay, and actually, there are very few uh, relations in physics which you will find popularly known. And Heisenberg uncertainty relation is one of that. And there is also a postal stamp, by by German Post. Which they came up with on the 100th birthday of Heisenberg. And what you notice here is that it says delta P, delta Q is of the order of H. Okay. So originally Heisenberg used semi-classical reasoning. As you may know, he used, as you may have read in your textbook, some kind of gamma ray microscope to determine the position of an electron. And in the process of measuring, it will disturb the position of electron. And so there is some error in measuring the position, and will lead to some disturbance in the momentum of the electron. Momentum. Okay. So basically, what Heisenberg said, that more accurately the position is known of a particle, the less accurately is the momentum determined, and vice versa. Okay. And actually, as I was saying just a while ago, these kind of relation which he obtained, they are more like often some kind of error disturbance like situation. Okay. Although we can recast his relation as some kind of error in position measurement and error in momentum measurement, and their product has to be larger than, say, of the order of Planck constant. But this approach is slightly semi-classical, and it is leads to a new sets of uncertainty relation which are known as error disturbance. So when you are measuring a position, you will be measuring a position with some error, and there is some disturbance in momentum. Okay, so now there is a whole set of people who have worked on these kind of uncertainty relations. Okay, but actually it is more than that. These relations actually capture. Okay, if we go beyond how these relations came into being, then you will see its physical content is actually quite different nowadays if you want to interpret it. And these relations actually capture inherent uncertainty or indeterminacy, or you say randomness, which is associated with a quantum system. So this is inherent, in a quantum system, and measurement has not to be measurement is not necessarily involved. Okay, if you want to involve measurement, it will lead to Heisenberg type of relations, which are error disturbance type of relations. So you can take out the measurement part from these uncertainty relations. Okay. Actually, as some of you perhaps were asking also earlier, in quantum mechanics, actually measurement you cannot. It is not defined how you measure. There are only many models see how measurement process can take place. So if you want to have a relation uncertainty relation based on measurement, then you have to have some model of measurement also. Okay, how actually measurement is taking place. Okay, and Heisenberg used some, as we all know, some kind of semi-classical reasoning, not semi-classical way of measuring, of some position. Okay. Nowadays, actually, we can think slightly more general terms. So whatever Heisenberg asserted, we can restate as that more information there we know about one particular quantity, lesser information can be obtained about a quote unquote complementary quantity. Okay. So in this form, this relation has transcended its original, scope. And basically, some people will take the view that this relation actually puts some kind of limit on the knowledge that we can gain about a system. So this also some kind of limits, a limit on what can be known. Okay, so these relations, I mean, okay, if I mean you all know about this relation, but this is the first form. This delta p dot delta q is of the order of h. That you can say that the most primitive form of uncertainty relation. Okay, but these relations have now become sort of marker of quantum features of a system, and it is often used to separate classical from quantum. When Heisenberg derived his relation, he did not use any specific quantification of uncertainty. Okay, you say I mean there is an error when you measure the position, but how you quantify this error? Okay, Heisenberg didn't say much about this how to quantify, because he used some particular thought experiment and came up with he used certain phrases which I will mention in a while. Okay. So, one has to use some specific measure of this uncertainty in the measurement of any physical observable. And depending on what you use as a measure of uncertainty, nowadays you will find there are hundreds of papers, which use different, widely different measures of uncertainty. And then there is a whole literature on that type of measure of uncertainty and uncertainty relation. Okay, so as I was just saying, he had some thought experiment, and he, was interested only a set of observable position and momentum of a particle, in particular an electron. So he was more interested, as I was saying in the very beginning, because there was a tussle, between this wave mechanics and matrix mechanics. So he was more interested in what this wave mechanics could mean. So he was more interested in understanding what is the physical content or visualization content or intuitive content. I mean, there are many different translations of his German phrases. So he was more interested in that. He was not interested in more exact mathematical formulation of this indeterminate. So if you want to have more, if you want to have a more exact mathematical formulation, then you have to do more than what he did. More than 100 uncertainty relations. Okay, and if you think of as some kind of, if you interpret it more broad.
Hello. Hello. Is the voice lost? Yeah, exactly. I think we lost. I think probably he lost connection. So can we call him by? Do you have a number? Maybe we can. Okay. His connection is lost. Yeah, he's logged out now. Probably Professor Panigrahi has his number. Maybe if you have an access, you can. Yeah. Then we can call him and find out.
Hello. I mean, I'm sorry. I mean, there was some network.
Yeah.
Okay.
Perfect. Okay.
I will share my screen again.
Yeah.
Just 1 minute. I will share my screen.
Sure.
Can you see it, or do I have to share it again?
As of now, I don't see it as of now.
Sure. I will share it again. Sure.
Yeah. Okay.
Now I think perhaps you can see.
Yes, it is here. Yeah. Yeah, perfect.
Okay. So sorry about this interruption. I think there can often be, as we all know, network related issues.
So this is another classical uncertainty, right? Right. Please go ahead.
Yeah. I mean, in classical systems also you could have. Right. Okay. So as I was just saying, depending on how you form